Hello students, with me, Miss Yessica. Today we're going to learn about the transport systems in mammals. Animals, particularly relatively large animals like mammals, are far more active than plants. They rely on locomotion to find food since they cannot manufacture it on. And this is energy consuming. For example, for the contractions of the muscles, it needs energy. A nervous system is needed to coordinate activity and sending nerve impulses is also energy consuming. Large brains consume large amounts of energy. So from that we know the greater the activity, the greater the demand for oxygens for respirations. So the transport system for oxygens in mammals have evolved unlike in plants. The larger and more complex animals become, the greater the demands on the transport systems. All animal cells require a supply of nutrients, such as glucose, for the metabolisms to produce the energy. Most living cells also need a constant supply of oxygens. Besides that, there will be also waste products, such as the carbon dioxide, to be disposed of. So basically, the functions of the transport systems in mammals are: first, it circulates the oxygens, carbon dioxide, nutrition, hormone, and many metabolites, including the enzymes, in the body. Second, homeostasis, maintaining the body temperature, pH. And the last one is facilitating the immune systems. So this is the pictures that shows the general layout of the main transport systems of mammals. The blood systems, or we know it as the cardiovascular systems, it made of a pump, the heart, and the systems interconnecting tubes, the blood vessels. The blood always remains within these vessels, and so the system is also known as a closed blood system. There are two classifications of transport systems in mammals. The first one is the artery systems. The second one is the vein systems. So for the artery systems, it brings the oxygen-rich blood and metabolism products to the body. Except for the artery that circulates to the pulmonary, it brings the blood that contain less oxygens. And the second one is the vein systems. It carries the carbon dioxide rich blood and metabolism waste to the heart. Except for the vein from the pulmonary, it carries the blood that contain lots of oxygens. The next one, we are going to learn about the cardiovascular pathway. So there are two cardiovascular pathway. The first one is the pulmonary circuits. The second one is the systemic circuits. So firstly, we're going to discuss about the pulmonary circuits. So the pulmonary circuits, it circulates the blood through the lungs. And how this is worked? Firstly, the blood from all regions of the body will circulate to the right atrium. After that, to the right ventricle, and after that to the pulmonary trunk, pulmonary arteries, and in the sides, the carbon dioxide will diffuse out of the blood, and then the oxygens will diffuse into the blood. And then this blood that contain the oxygens will circulate to the pulmonary venules, after that to the pulmonary veins, and at the end it will enter the left atrium in the heart. So the second one is the systemic circuits. It serves the needs of the body tissues. So how this is worked? So the blood from the superior and inferior vena cava will circulate to the right atrium, and after that to the lungs, the left ventricle, to the aorta, and then after that to the organs and the major body regions, and then next to the superior or inferior vena cava, and at the end it will enter the right atrium of the heart. So these combinations of the pulmonary circuits and then the systemic circuits, it makes the double circulatory systems. The mammalian circulatory systems is therefore a closed double circulation. So since you have mentioned about double circulations. So in this slide, we're going to discuss about the single circulations and the double circulations. So to give you a brief introductions, what is the single circulation and what is the double circulation? Firstly, fish, they have a single circulation. And the birds and mammals, they have a double circulations. And then what is exactly the single circulation and double circulations? We're going to see that in the next slide. So the first is the single circulatory systems. So animals with the closed circulatory systems. Okay, so what is the closed circulatory systems? It means that the blood, they circulates in the vessels. So this is what we call as the closed circulatory systems. So it can be either the single circulations or a double circulations. And a single circulation is found, for example, in the fish. And then what exactly these circulations do? Okay, first, the heart pumps the deoxygenated blood to the gills. And here, the gases exchange takes place. The second one, there's a diffusion of the carbon dioxide from the blood into the water that surrounds the gills, and then the diffusion of the oxygens from the water into the blood. So if you trace the journey of the blood around the body, beginning in the left ventricle of the heart, you'll find that the blood travels twice through the heart on one complete circuit. Many animals, including all the vertebrates, they have a closed circulatory systems in which the blood is enclosed within the tubes, like I have mentioned before. This generates a higher blood pressures as the blood is forced along a very narrow channels instead of flowing into large cavities. This means the blood travels faster, and so the blood systems is more efficient at delivering substances around the body. So animals that have the closed circulatory systems, the blood leaves the heart under the pressure and flows along the arteries and then to the arterioles or the small arteries and then next to the capillaries. So next, the blood leaves the heart under pressures and flows along the arteries and then the arterioles or the small arteries to the capillaries. Next, there are extremely large number of capillaries. These come into the close contact with most of the cells in the body, where substances are changed within the blood and the cells. After passing along the capillaries, the blood returns to the heart by means of the venules, or the small veins, and then the veins. Valves ensure that the blood flows only in one direction. So the valves in the veins, the functions is to ensure that the blood flows only in one direction. Please remember that. So animals with closed circulatory systems, they are generally larger in size and often more active than those with an open systems. The passage of the blood through the heart. So how the blood circulates through the heart. So firstly, the blood that contain less oxygens from the superior vena cava and inferior vena cava will enter the right atrium. After that, the right atrium sends the blood through an atrioventricular valve or to the right ventricle. After that, the right ventricle sends the blood through the pulmonary semilunar valves and then next to the pulmonary trunk, and after that it divides into two pulmonary arteries and the next to the lungs. So the blood that contain loads of the oxygens from the four pulmonary veins will enter the left atrium. The left atrium sends the blood through an atrioventricular valve to the next ventricle. The left ventricle sends the blood through the aortic semilunar valve into the aorta and then to the body proper. In the slides, we are going to discuss about the blood vessels, the structures, and then the functions. The vessels making up the blood systems are of three main types. Vessels carrying the blood away from the heart are known as the arteries, while those carrying blood towards the heart are veins. Linking arteries and veins taking blood close to almost every cells in the body, are the tiny vessels called the capillaries. The first blood vessels is the artery. So the arteries it carry blood away from the heart to the capillaries. The structures of the wall of the artery enables it to perform these functions efficiently. The arteries and veins they both have walls made of the three layers. So the first is the inner endothelium or the lining tissues called the tunica intima, made of a layer of flat cells or squamous epithelium fitting together like jigsaw pieces. This layer is very smooth, minimizing the frictions with the moving blood. The second is the middle layer called the tunica media or the middle coat, containing the smooth muscles, collagen, and elastic fibers. The third is another layer called the tunica externa or the outer coat, containing elastic fibers and collagen fibers. As arteries reach the tissue to which they are transporting blood, they branch into smaller and smaller vessels called the arterioles. The walls of the arterioles are similar to those of the arteries, but they have a greater proportions of the smooth muscles. These muscles can contract, narrowing the diameter of the arteriole and so reducing the blood flow. This helps to control the volume of the blood flowing into tissue at different times. For example, during exercise, the arterioles that supply the blood to the muscles in your legs will be wide or dilated as their walls relax, while those carrying the blood to the gut's wall will be narrow, or we call it as the constricted. The distinctive characteristic of an artery walls are its strength and elasticity. Blood leaving the heart is at a very high pressure. Blood pressure in the human aorta may be around 16 kilopascal. To withstand such pressure, the artery walls must be extremely strong. This is achieved by the thickness and compositions of the artery walls. Arteries have the thickest walls of any blood vessels. The aorta, the largest artery, have an overall diameter of 2.5 cm close to the heart, and a wall thickness of about 2 millimeters. Although this may not seem very great, the compositions of the wall provide great strength and resilience. The tunica media, which is by far the thickest part of the wall, contain large amounts of the elastic fibers. This allows the wall to stretch as pulses of the blood surge through at high pressure. Arteries further away from the heart have fewer elastic fibers in the tunica media, but they have more muscle fibers. The elasticity of the artery walls is important in allowing them to give, which reduces the likelihood that they will burst. This elasticity also has another very important functions. Blood is pumped out of the heart in pulses, rushing out at high pressures as the ventricles contract and slowing as the ventricles relax. The artery walls stretch at high pressure, blood surges into them and then recoil inwards as the pressure drops. Therefore, as blood at high pressure enters an artery, the artery becomes wider, reducing the pressure a little. As blood at lower pressure enters the artery walls recoils inwards, giving the blood a small push and raising the pressure a little. The overall effect is to even out the flow of the blood. However, the arteries are not entirely effective in achieving this. If you feel your pulse in the wrist, you can feel the artery. Even at this distance from the heart, being stretched outwards with its surge of blood from the heart. As blood leaves the capillary bed, the capillaries gradually join one another, forming larger vessels called the venules. These join to form the veins. The function of the veins is to return the blood to the heart. By the time blood enters the vein, its pressure has dropped to a very low value. In humans, a typical value of venous blood pressure is about 5 millimeter Pascal or less. This is very low pressure, means that there's no need for the veins to have the thick walls. They have the small three layers as arteries, but the tunica media is much thinner and has a far fewer elastic fibers and muscle fibers. The low blood pressures in veins creates a problem. How can this blood be returned to the heart? The problem is perhaps most obvious if you consider how blood can return from your legs. Unaided, the blood in your leg veins will sink and accumulate in your feet. However, many of the veins run within or very close to several leg muscles. Whenever you tense these muscles, they squeeze inwards on the veins in your legs, temporarily raising the pressure within them. This squeezing in itself will not help to push the blood back towards the heart. Blood would just scooch up and down as you walk. To keep the blood flowing in the right directions, veins contain a half moon valves or semilunar valves formed from their endothelium. These valves allow blood to move towards the heart, but not away from it. Thus, when you contract your leg muscles, the blood in the veins is squeezed up through these valves, but cannot pass down through them. Note that blood samples are normally taken from the veins rather than from the arteries because of the lower pressure in them. The arterioles themselves continue to branch, eventually forming the tiniest of all blood vessels, capillaries. The function of capillaries is to take blood as close as possible to all cells, allowing rapid transfer of substances between cells and blood. Capillaries form a network throughout every tissue in the body except the cornea and the cartilage. Such networks are sometimes called capillary beds. The small size of capillaries is obviously of a great importance in allowing them to bring blood as close as possible to each group of the cells in the body. A human capillary is approximately 7 micromillimeter in diameter, about the same size as the red blood cells. Okay, how amazing is this? Moreover, the walls of the capillaries are extremely thin, made up of only a single layer of endothelial cells. As red blood cells carrying oxygen squeeze through a capillary, they are brought to within as little as 1 micrometer of the cells outside the capillary which need the oxygens. In most capillaries, there are tiny gaps between the individual cells that form the endothelium. As we shall see later in this unit, these gaps are important in allowing some components of the blood to seep through into the spaces between the cells in all the tissues of the body. These components form the tissue fluid. By the time blood reaches the capillaries, it has already lost a great deal of the pressure originally supplied to it by the contractions of the ventricles. As blood enters the capillary from an arteriole, it may have a pressure around 4.7 kilopascal. By the time it reaches the far end of the capillary, the pressure will have dropped to around 1.3 kilopascal. So what you need to remember about the blood vessel is the capillaries are small and extremely numerous, estimated about 6,300 square meter. And the artery and veins, they have a different structures. Artery, they have a thick wall, while the vein, they have a thin wall. Arteries and veins can easily be distinguished, as shown in this figure below. The walls of blood vessels contain collagen, a tough, fibrous proteins which makes them strong and durable. They also contain elastic fibers which allows them to stretch and recoil. Smooth muscle cells in the walls allow them to constrict and dilate. So the key differences between the arteries and veins are, arteries has a narrow lumen. They also have a thicker walls. they have more collagen, elastic fibers, and smooth muscles, and they have no folds. While for the fins, they are the opposites, which are they have a wide lumen, thinner walls, less collagen, elastic fibers, and smooth muscles, and most importantly, they have the folds. So that's all for today. Thank you for your attention and goodbye, students.